Hello and welcome to 8.5 Vectors in the Cartesian Planes. We're talking about vectors today. A new concept for probably everybody. Scalars, single numbers representing only magnitude. A scalar like number 2, 5, just a single number. Examples of scalars, quantities such as length, area, mass, price, and temperature. Now vectors are different than scalars because vectors are quantities that represent magnitude and direction. So there's a magnitude to them and a direction. They're going this way, they're going vertical, they're going down. Examples of vectors are force and velocity. Vectors are represented as directed line segments with 2 points, the initial point and the terminal point. So here's our initial point P, and here's our terminal point Q. So we have an initial point and a terminal point. It's directed, so there's an arrow showing it goes from the initial to the terminal. Shows that. So we usually identify the initial point as P, the place the vector begins. And the terminal point is usually identified as Q, the place where the vector ends. We could therefore represent a vector beginning at P and ending at Q in the following way. PQ with this line over the top looks like a ray in angles. So the arrows over the Q, that means Q is the terminal point. So the line begins at P and the arrows over the Q. And so it starts at P and ends at Q. We'll often identify vectors by assigning names such as U, V, and W. The book will show these in bold type. It's hard to show that when we're handwriting it, but when you look into the book, these will have a bolder look to them than the regular text. Vectors U and V are said to be equal if they have the same magnitude and the same direction. So this could be U, and then this could be V. They don't have to be on top of each other, but they have the same direction and the same magnitude, and the magnitude is the length. So magnitude of a vector, the length of a vector is called its magnitude, and is denoted with these double bars around it. The magnitude of a vector U is the square root of a squared plus b squared, where a is the horizontal displacement and b is the vertical displacement. There's my red pen. So A is a horizontal displacement, B is a vertical displacement. The zero vector is just 0. Okay, properties of vector addition and scalar multiplication. U plus V is V plus U, so it's commutative. U plus V plus W is U plus V plus W, so you could change the association. U plus 0 is U, and U plus negative U is 0. These, I underlined, it should have been a bold, so ignore the underlining. A times the vector U plus V is AU plus AV. A plus V, these are both scalars, times the vector U is AU plus BU. AB against scalars times U is A times BU, which is also B times AU. 1 times U is U, 0 times U is 0, and A times 0 is 0. The magnitude, let me rewrite this one. Should say the magnitude of AU is the absolute value of A times the magnitude of U. That's what that should say. So to add two vectors graphically, put the tip of one vector at the tail of the other vector. And we'd see that as, if here's U, here's V, this resultant vector is U plus V. So V is a vector, the negative V has the same magnitude but in the opposite direction. So if here's our v, then this is negative v. So I have the same magnitude in the opposite direction. If P is located at x1, y1, and Q is located at x2, y2, then U being PQ would be found by U equals, and this is kind of a, not a parenthesis, it's kind of pointed. That's the look here for the vector. x2 minus x1, comma, y2 minus y1. Okay. So with that, let's do an example. If P is located at negative 2, 4, that's our initial point, and Q is at 3, 7, that's the terminal point of the vector, find U equals PQ. So U will equal 3 minus negative 2, comma, 7 minus 4. So U will equal 5, 3. Now vector U could be defined in component form as U equals U1, comma, U2, where U1 is the horizontal displacement, in that case it's 5, and U2 is a vertical displacement, in this case it's 3. So vector operations using the components. Given two vectors, U equals U1, U2, and V equals V1, V2, and a scalar A, U plus V is U1 plus V1, comma, U2 plus V2, so we're adding the horizontal components and we're adding the vertical components. A times U is A times U1, comma, A times U2, so multiply A by each component, vertical, horizontal, and vertical. And the magnitude of U is the square root of U1 squared, that's a horizontal part squared, plus U2 squared. Okay, so use the figure to sketch 2U plus V. So I'll do 2U plus V over here, given what we have over there for U and V. Then we're going to do our negative 1/2 U minus V on this graph. So let's look at what is U. U is going to be the vector, it goes to the left 2, and it goes down 2. And V would be going to the right 1, 2, 3, 4, and then down 1, 2, 3, 4. So 2U plus V. 2U is going to be 2 times negative 2 is negative 4. 2 times negative 2 is negative 4. So if we start here, 2U is going to be going down. It's going to go to the right 4 and down 4. That's 2U. And V is going to be going to the right 4, 1, 2, 3, 4, and then down 4, 1, 2, 3, 4. So the resultant vector is there, 2U plus V. Let's come over to the next one. Negative 1/2 U minus V. So what is negative 1/2 U? Well, that's going to be negative 1/2 times negative 2, comma, negative 1/2 times negative 2. So negative 1/2 U is going to be 1, 1. And then negative V minus V is going to be the negative of 4, comma, the negative of negative 4. So negative V is negative 4, comma, 4. So negative 1/2 U is just going to be this. and then minus v, so minus v is going to go to the left 4, 1, 2, 3, 4, and then down 4, 1, 2, 3, 4. This is the result, negative 1/2 u minus v. Okay, I just noticed I did something wrong. Restate that. U is positive 1, 1. I did a positive 1, negative 1. So u should be up this direction. Then negative v should be 1, 2, 3, 4 to the right, and then 4 up. 1, 2, 3, 4. There we go. Negative 1/2 u minus v. So the result is this. Minus 1/2 u minus v. There we go. Okay, feel free to pause that. I'm going to move on to example 3 here. Example 3 tells us to find the component form and the magnitude of vector v for this. Okay. This is our vector v. What does it contain? We're going from here over 1, 2, 3, 4, 5, 6, 7. And then we're going 1, 2, 3, 4, 5 down. So 7 to the right, that's positive. So minus 5 because we're going down. That's our vector v. And the magnitude of vector v is going to be the square root of 7 squared plus negative 5 squared. That's 49 plus 25. That's the square root of 74. So the magnitude of vector v is the square root of 74. I'm going to move this up for example 4. And example 4 says find the component form and the magnitude of the vector defined by the points given below. So I'll call the first one u, and then the second one v. Here's our p, here's our q. Okay, so u is going to be 2 minus 1, comma 3 minus 6. So it's going to be 1, negative 3. And the magnitude of u is going to be the square root of 1 squared plus negative 3 squared, square root of 1 plus 9, which is the square root of 10. So we have the component form, 1, negative 3, and the magnitude for u. Now for v, we have the magnitude 0 minus 1, comma, 0 minus negative 6, negative 1, comma 6. Okay, and that's our component form. The magnitude of v is going to be the square root of negative 1 squared plus 6 squared. So it's 1 plus 36, or the square root of 37. Magnitude of v is 1, negative 6, and, sorry, the component form is 1, negative 6, and the magnitude is square root of 37. Okay, feel free to pause. I'm going to go on to the next one. Okay, calculate 2u plus v, negative u plus 3v, and negative 2v, for u being 4, 1, and v being 2, 5. So for A, we have 2u plus v. That's going to be 2 times 4, 1 plus 2, 5. So we're looking at 8, 2 plus 2, 5. So we're looking at 8 plus 2, comma 2 plus 5, or 10, 7. That's our final answer there. I'll just circle it or box it in. Okay. Now for B, we're looking at negative u plus 3v. That's going to be the negative of 4, 1 plus 3 times the 2, 5. So that's negative 4, negative 1 plus 6, 15. So that's going to be negative 4 plus 6, comma, negative 1 plus 15. And we get 2, 14. And C, we're looking for negative 2v. It's negative 2 times the 2, 5, which is going to be negative 4, comma, negative 10. Okay, we'll move on to example 6. Determine the component forms of negative u, 2u minus v, and u plus v, and find the magnitude of u and v. So first of all, what is u? U is going up. 1, 2, 3, 4. So I should have done the other one first. It's going to the left, 1, 2, 3, 4, then up, 1, 2, 3, 4. So it has the component form of negative 4 because it goes to the left 4, comma, positive 4 because it goes up 4. And v, it's going 1, 2, 3, 4, 5, 6. So the horizontal part is positive 6, then it's going down 1, 2, 3, down. So it's going to be 6, negative 3. Go 6 to the right, 3 down. So our first part, we want to find negative u. That's going to be the negative of negative 4, 4. And that's going to be 4, negative 4. Then we want to find 2u minus v. That's going to be 2 times the vector negative 4, 4, minus 6, negative 3. And we just distribute that, so it's going to be negative 8, 8, minus 6, negative 3. So negative 8, minus 6, 8, minus negative 3, and we get negative 14, 11. For u plus v, we have negative 4, 4, plus 6, negative 3. That's going to be negative 4 plus 6, 4 plus negative 3. And we end up with 2, 1. Box, that's our final answer. Here's a final answer. Okay, last two parts, we need to find magnitudes of u and magnitude of v. The magnitude of u is going to be the square root of negative 4 squared plus 4 squared, square root of 16 plus 16, square root of 32, which is 4 times the square root of 2. And the magnitude of v is going to be the square root of 6 squared plus negative 3 squared. That's square root of 36 plus 9. square root of 45, which is 3 times the square root of 5. That was a lot. Okay, so we found our negative u, we found 2u minus v, we found u plus v, the magnitude of u, the magnitude of v. A couple of the concepts before I move scroll the screen or the page. The unit vector is a vector with a length or magnitude of just 1. That's a unit vector. There are two commonly used unit vectors. I, this is not the imaginary number I. This is in vectors. I equals 1, 0, and j is 0, 1. So I is a unit vector in the horizontal direction. J is a unit vector in the vertical direction. I and j are two unit vectors parallel to the coordinate axes. So parallel to the x-axis, parallel to the y-axis. These two unit vectors are very useful because any vector can be written in terms of I and j. Oh, drop that eraser. So if we have a vector AB, where A is a horizontal, B is a vertical, we can say A times 1, 0 plus B times 0, 1. And 1, 0 is I, 0, 1 is J, so it's AI plus BJ. So 4, 1 could be written as 4I plus J. So this expression in terms of I and J is an example of what we call a linear combination. And linear combination is any sum of scalar multiples and vectors. So we have scalar multiples in the vector. Scalar multiple here would be 1. Here we are. To construct a unit vector from a vector u, we must multiply it by a scalar that is equivalent to the reciprocal of the vector's magnitude. So consider the following vector. AU, the magnitude of AU is 1. That's the absolute value of A times the magnitude of U is 1. So I should say A equals 1 over the magnitude of U. A would be 1 over the magnitude of U. So if you multiply your vector by that, you'll end up with a unit vector. So note the absolute value sign around the A has been dropped in the third equation, since we know in advance that we want to multiply U by a positive number. And this is going to be positive. Okay, given U equals 1, 4, find a unit vector pointing in the same direction as U and the linear combination of I and j that is equivalent to U. So let me scroll up the screen a little bit. There. Okay, first the magnitude of U is going to be the square root of 1 squared plus 4 squared. Square root of 1 plus 16, which is the square root of 17. So for part A, we'll do 1 over the square root of 17 times U, which is 1 over the square root of 17 times the vector 1, comma 4, which is 1 over the square root of 17, comma 4 over the square root of 17. And yeah, I'm going to leave it like that. I'm not going to rationalize that denominator. The second part, it says to find the linear combination of I and j that's equivalent to U. So for part B, we know it's 1, 4, and that would be 1 times I plus 4 times j, which is I plus 4j. Now we can go even further with vectors. We can split them up a little more. So we're going to see here. Okay, so here's our vector u, has a magnitude of u there. It's the direction of it. This side could be considered as the magnitude of u times sine theta, and this would be the magnitude of v, I should say magnitude of u, times cosine theta. So the horizontal part would be the magnitude of u times cosine theta, and the vertical part is the magnitude of u times sine theta. So you can write a vector in terms of its magnitude times, for the horizontal part, cosine theta, and the vertical part, sine theta. So for example 8 here, find the magnitude and direction angle of vector v. The first one, it's kind of in the format already that we need, because it's v equals the magnitude of v times cosine of theta, comma, sine theta. Well, this could be rewritten as 7 times cosine 45 degrees, comma, sine 45 degrees. So that means that the magnitude of v must be 7, and the angle theta must be 45 degrees. What we're seeing here is a vector, 45 degrees from the horizontal, going in that direction, a length of 7. For the next one, we're going to have to do a little bit of work. Let's draw a little picture of what we're seeing here. -2, -2 puts us down here. So the magnitude of v is the square root of -2 squared plus -2 squared, square root of 4 plus 4, square root of 8, which is 2 times the square root of 2. Now, tangent theta, I'm going to do theta bar, because that would mean a reference angle. This reference angle here, theta bar, is going to be -1 over -1, which is 1. So theta bar would be 45 degrees. But this is clearly not 45 degrees because 45 is up here. So it's 180 degrees plus the 45 degrees. So theta would be 180 degrees plus 45 degrees. So theta would be 225 degrees. So the magnitude of v is 2 times the square root of 2, and theta would be 225 degrees. On to the last page for this section. Okay, find the component form of v given its magnitude and the angle it makes with the positive x-axis. So its magnitude is 4 times the square root of 2, with theta is 45 degrees. So v is going to be 4 times the square root of 2 times cosine 45 degrees, comma, sine 45 degrees. That's going to be 4 times the square root of 2 times the square root of 2 over 2, comma, square root of 2 over 2. So that's going to be 4 times the square root of 2 over square root of 2 over 2, comma, 4 root 2 times square root of 2 over 2. So we end up with 4, 4. And component forms of 4i plus 4j. Linear combination form there. That wasn't so bad. Less work going into that form than the other. Now if you take physics, you're going to be getting to do some more vectors. golf ball is driven into the air at a speed of 75 miles per hour with an angle of 50 degrees from the horizontal. Express this velocity in vector form. So we have is 75 miles per hour, and this is 50 degrees. So V would be 75 times cosine of 50 degrees, sine of 50 degrees. V is 75 times what? I'll say 75 times cosine 50 degrees I plus 75 sine 50 degrees J. So put this in the calculator, you're going to end up with 48.209 I plus 57.453 J. And in component form, 48.209 comma 57.453. So what this means is, in the horizontal direction it's going 48.209 miles an hour. In the vertical direction it's going 57.453 miles per hour. If you measured it directly head on from this, you're going to see the 57. But let's just say here, if you put a radar gun here and you took the reading, it's reading that it's doing 48. If you put the radar gun above it, it's going to read that it's doing 57. So you can kind of see, depends on your angle, it could affect what the speed's going to show up to be. That's something that police officers have to consider when they're using their radar guns or lasers. Okay. A boy is pushing a toy truck across the floor. If the toy weighs 3 pounds and the boy is exerting half a pound of pressure on the toy, what is the total force being applied to the toy truck? Let me draw a picture of a truck. I can draw a pickup truck for this. Maybe they mean it's supposed to be like a big rig, I don't know. So the boy is pushing the truck with 0.5 pounds of force. The truck being pulled to the earth as 3 pounds of force. So our force vector would be 0.5 I minus 3J. Why minus 3? Because it's going in the down direction. It's minus 3. So our magnitude of the force is going to be 0.5 squared plus 3 squared. It's going to be 0.25 plus 9. Square root of 9.25. And that's approximately 3.04 pounds. The total force being active on this truck. 0.5 from the boy, 3 from the earth. So overall 3.4 pounds in the resultant vector. And that's it. That'll be the end of this section. Okay, let me know if you have questions. Thanks.